Now in this lesson, we are going to solve one problem on Bohr model. The question is, what will be the kinetic energy, potential energy and total energy in the first and second orbit of hydrogen if potential energy in the first orbit is taken to be 0. So this is the question. We have to find kinetic energy, potential energy and total energy in the first and second orbit of hydrogen if the potential energy in the first orbit is taken to be 0. So this is given as 0 and we have to find out for the first orbit and the second orbit. So what will be these values? So first we think of actual values. What are the actual values? In electron volt of kinetic energy, potential energy and total energy, all in electron volts. In the first orbit, what is the total energy? Minus 13.6 electron volt, right? E1 is equal to minus 13.6 electron volt. Kinetic energy is minus of total energy. So this will become plus 13.6 eV. And potential energy is 2 times total energy. So that becomes minus 27.2 electron volt. Right? This we know. Kinetic energy is minus of total energy and potential energy is 2 times total energy. What about the second orbit? Energy in the nth orbit is E1 by n square. So divide this by 2 square. So what will you get? Minus 3.4 electron volt. And this will be minus of this. Therefore, 3.4 electron volt. And potential energy is double of this. So we get minus 6.8 electron volt. These are actual values. But now in the problem it is told that this is 0. So what will happen to this and this? So what will be kinetic energy? Kinetic energy? No, don't think it is 0. Then all will be 0. So that is not what is correct. Right? Please understand, if we change the reference line for potential energy, kinetic energy values don't get affected because kinetic energy depends on velocity. So it's not going to affect whatever we call the baseline of potential energy. It's not going to get affected. Let's consider this situation. Suppose this is a nice lake, right? Nice water. And some bird is flying here, right? With some velocity v, right? Nice beautiful lake in a nice place, some bird is flying there with velocity v. If you measure the potential energy of the bird with respect to this place, and suppose this height is h, then the potential energy will be mg h. Right? Simple. If you measure the potential energy of this bird with respect to this one, bottom of the lake, its potential energy will be mg into capital H. This is the different h and that is more. So potential energy varies depending on what we are calling potential energy equal to 0. But whatever we do, the kinetic energy is always half mv square. Right? It does not change. Therefore, we have changed the reference line for potential energy. We have made it 0. But kinetic energy will remain as it was, 13.6 eV. What happens to total energy? No, total energy will not be this. Now total energy is sum of these two energies. That will be again 13.6 eV. What happened to our relationship? K equal to minus E, U equal to 2E. Those relationships are not valid anymore. That relationship holds true only when we take absolute potential energy values. We take U at infinity to be 0. Then you can apply all those equations. But here you cannot apply. So therefore, the kinetic energy remains unchanged because that depends on velocity, not from where you are measuring potential energy. And total energy is always sum of kinetic energy and potential energy. All these values anyway are in electron volt. Now how to find the values for the second orbit? Again look at that example. Suppose something else is flying here at a different height. Suppose this height is h dash. So potential energy will be mg h dash. Right? The potential energy of this one with respect to ground is say mg capital H dash. But what is the potential energy difference between the potential is measured from here and here? That is equal to mg and whatever is the height of the lake, say y. Now this mgy is the difference between the potential energy of this measured from here and measured from here. And same thing is true here. So when you change the reference line for potential energy, all potential energy values increase or decrease by the same amount. This is very important to understand. When you change the reference line for potential energy, all potential energy values increase or decrease by the same amount. Now how this has become 0? Earlier it was minus 27.2. So if you add plus 27.2 to this number, you get 0. So this potential energy value is increased by 27.2. So this one also must increase by the same amount. So we get minus 6.8 plus 27.2 and that gives you 20.4. Right? So that's how you get the new potential energy here. Remember, when the reference line for potential energy change, all potential energy values increase or decrease by the same amount. What will happen to kinetic energy? Kinetic energy does not depend on this. So it will remain as it is 3.4. And about total energy, sum of these two. So 23.8 electron volt. So please learn some important concepts from this problem. First important concept is K equal to minus E and U equal to 2E is valid only when we are looking at absolute potential energy values. That means U at infinity equal to 0. Here we cannot apply that. Second thing, when you change the reference line for potential energy, all potential energy values increase or decrease by the same amount. So this one increased by 27.2, this one also increased by 27.2. And the third important thing we learned was that even if we change the reference line for potential energy, kinetic energy values are not going to get affected because they depend on speed, half mv squared. So whether you change the potential energy reference line, these are not going to get affected, they will remain as they were earlier. So this is very important to understand. Earlier we have learned that when a body is moving in a circular orbit, under the action of a force that obeys inverse square law, like electrostatic force and gravitational force, that is for electrons moving around nucleus or for satellites moving around Earth, the relationship is K equal to minus E and U equal to 2E. This relationship is valid only when we are looking at absolute potential energy values. Keep this in mind always. In this lesson, we are going to solve one more problem on Bohr model. A small particle of mass m is moving in a circular orbit such that its potential energy U is equal to AR square, where A is a constant and R is the distance of the particle from the center of the circular path. The question is, using Bohr's model of quantization of angular momentum, find the radius of the nth allowed orbit. Now potential energy is given as a function of R. To get force in this kind of situation, just differentiate potential energy with respect to R and put a minus sign. So what will you get? Very easy differentiation, all of you know this. This will be minus 2AR. This minus sign shows that the force is attractive, and this force provides the necessary centripetal force. So mod of F, which is 2AR, will be equal to mv square by r. Right, the electrostatic force of attraction provides the necessary centripetal force. An electron is moving around the nucleus. Here somebody is providing force, and that force is equal to mv square by r. So this is one equation. Second equation we get from Bohr model of quantization of angular momentum. Right? You know that mvr is equal to nh by 2 pi. Right? So now from this equation we can get velocity and put it in this equation, and then we will find the equation for radius. So velocity from this equation is nh by 2 pi mr. Right? Put this in this equation. What do you get? 2AR equal to m by r v square, square of this, so n square h square by 4 pi square m square r square. So now to find r, you have got r here, r square, r. So we will get r to the power 4. So whatever we get, we will take 4th root that side. Now what do you get here? Now we get r, all the r's have come this side. One m will get killed, right? So what do you get? N square h square by 8, right? 4 into 2, 8, pi square am whole to the power 1 by 4. So this is the answer to this question. A particle was moving in a circular orbit. Potential of the energy of the particle was given as U equal to AR square. Once you know potential energy, you take the derivative with respect to R here. You will get force F equal to minus du dr. The minus sign just shows an attractive force. We are not bothered about it right now. So mod of this force is 2AR. This force provides the necessary centripetal force. For anything to move in a circle, we need a centripetal force. So we got this equation. Bohr's model of quantization of angular momentum tells us that mvr is nh by 2 pi. So from here you get the equation for v. That v you put it in this equation, and then you simplify and get the radius of the nth allowed orbit. Very simple. Now we look at one more problem on Bohr model. An imaginary particle whose charge is same as that of an electron but mass is 100 times is moving around a nucleus of charge plus 4e. Question is, find the radius of the nth allowed orbit. We know for the hydrogen atom The radius of the nth allowed orbit is given by this formula. Radius is epsilon naught n square s square by pi me square. Now when the mass of the particle becomes 100 times, this will be replaced by 100 m. Right? And when you go from hydrogen to hydrogen-like, E square is replaced by Z square in every formula. So here Z is 4. So therefore, we can easily write the equation for radius epsilon naught n square h square divided by pi. Mass has become 100 times, so 100 m, and this is 4e square because Z is 4. And the answer is therefore epsilon naught n square h square by 400 pi me square. As simple as that. Now, in the second part of the question is find the wavelength of the emitted photon when this particle jumps from 4th orbit to 2nd orbit. Suppose this was hydrogen and there are no complications, then 1 by lambda is given by R 1 by nf square minus 1 by ni square. You know that, right? Now when you go from hydrogen to hydrogen-like, R gets replaced by Rz square. So 1 by lambda will be R z square 1 by nf square minus 1 by ni square. Now there is one more complication here. Mass of the particle has become 100 times. If mass becomes 100 times, then energy will become 100 times. If energy becomes 100 times, frequency will become 100 times and wavelength will become 1 by 100 times. So please remember that. If the mass of the particle is becoming 100 times, the energy becomes 100 times, frequency becomes 100 times, wavelength will become 1 by 100 times. So we can calculate wavelength from here and then divide that by 100. So let's do that. 1 by lambda equal to R. Z here is how much? Z is 4. So 4 square. The final orbit is 2 minus the initial orbit here 1 by 4 square. So you will get 16 LCM here. This 16 will get killed by this 16. So 1 by lambda will become, this will become 4 minus 1, 3. So you will get 3R. Lambda becomes 1 by 3R. Okay, remember 1 by R is 0.911 into 10 to the power minus 7 divided by 3. So this gives you lambda if the particle were an electron, but mass has become 100 times. So wavelength will be 100 times less. So what do you get lambda for this imaginary particle? We will divide this by 100. So 0.911 into 10 to the power minus 7 by 3, and that gives you the answer as 0.3 nanometer. So what important thing we have learned in this problem? If we are given an imaginary particle, then the energy will be getting multiplied by the factor by which the mass is more than the mass of electron. So mass has become 100 times. So energy will become 100 times. Frequency will therefore become 100 times. Wavelength will become 1 by 100 times. And the other important thing we have learnt is that when you go from hydrogen to hydrogen-like, replace E square by Z square in every formula. And that's how you solve these kind of problems, especially in JEE Advanced. They try to complicate the problems by giving you some imaginary particle whose mass may be different, charge may be different. So you should know how to handle these kind of problems.